All right, so here we go with section 16.3 here, or 17.3 in the book. So the first thing to remember is this, that remember last year when you had something called the Fundamental Theorem of Calculus, part 2, and that was when basically you learned that when you have boundaries on your integral, when you have bounds right there, that when you do the integral, then you plug in b minus, and then plug in a. And so big F is denoting, like, the integral. So it's the function before this one right here. Because remember, if you go from here to here, then this is the derivative over here. So little f is the derivative of big F, because when you do the integral, that's the opposite direction. Okay? So, or basically the antiderivative also. Okay? So in other words, if you ever had something that was already the antiderivative right here, the integral and the antiderivative, they kind of like knock each other out, like those cancel out, and you basically are plugging in b and a into your original function. So you did those a little bit, and anyway. All right, so just remember that because you'll see it in a second. So this first little bit right here, I already filled this out because I just wanted you to see. I didn't want it to be so grueling to notice here. But a vector field is a vector field F that is the gradient of a scalar field is called a conservative vector field. That's like an important definition. All right. So let's begin an example in which the line integral of a conservative vector field is evaluated. So this vector field down here is conservative, meaning it was the vector field that we're given right here, it is already the derivative of some other thing that came before it. So you don't know what came before it. We're going to find that out later, or we're going to see how to do that later. But this information right here is already the derivative of something else. So this is the derivative with respect to x of some other function, and this is the derivative with respect to y of some previous function. Okay, so that's what makes it conservative. All right, so find the work done by this field, force field, on a particle that moves from 0, 0 to 1, 1 along these paths. So here's our paths down here. There are 3 different paths. We're starting and we're ending in the same place, but we're just getting there different ways. One's just a straight line, one's just a curve of x equals y squared, one's the curve, let's see, y equals x to the third. Okay, so you can see those there in the parametric form. All right, so we're going to calculate the work for each of these paths that we have down here. All right, so here's the first one. So this is my path, TT, it just went up and over, okay? And so I basically plug those things into my function right here. So t and t makes my t squared, I got my 1/2, and then 1/4 t squared. So plugging this into here, that is my f of rt, so that's right there. And then I have to do the derivative, all right? So my derivative over here, my derivative with respect to x would be 1/2 y. And my derivative with respect to y over here would be, wait a minute, I'm supposed to be doing, oh no, I'm sorry, not those derivatives, duh. I'm supposed to be doing the derivatives of this thing right here, r of t. I got confused for a second. All right, so those derivatives are both 1, so that's why it's 1, 1. Sorry about that. All right, so do my dot product. When I dot these together, I get this expression down here. So 3/4 t squared is what I'm integrating. That integral comes out to 1/4. All right, so down here we have a new path. So this is the path, this curve going to the side. That's like basically x equals y squared, if you're going to think of it in Cartesian coordinates. So same thing, plug t squared into my problem here, plug t squared in t, so I get t to the third. That's how that's coming about. Then t squared and t plugged into there, so t squared squared is t to the 4th. All right, and then this time the derivative here is 2t and 1. So there it is. Dot product it, get me here. And look at that, same answer. Okay, now we do it again, all the same process again, dot product it, get this one, and looky there, same answer. So, therefore, the work done is the same in each case. So, this is a special result. So this happens, the work done is the same if you're going from the same beginning place to the same ending point if you have a conservative vector field. Okay? If your vector field is already conservative, meaning it was the derivatives of some previous field or some previous equation there. Okay? All right. So in this example, note that the vector field is conservative because this function must have been the derivative, must have been del f of something else. So look here, this was the function. So let's take a look. What's the derivative with respect to x? 2 times 1/4 is 1/2, and then x goes to x squared goes to x, and then you got your y. So there it is. And then what's the derivative with respect to y? Well, the y goes away to 1, and there's your derivative right there. So that was the function that came before this guy right there. So yeah, so you don't know how to find that yet, but later you will do that. Okay, so in such cases, the following theorem states that the work done is basically you're going to be able to do this. F of x1, y1 minus f of x0, y0. So basically what you can do is plug in the terminal point into your function minus plug in the initial point. But that's only if you know the function. So that can only happen if you know this thing. So if you know this, then you don't have to do all this mess up here. You can just do this work here. So f of x1, y1, so that would be, if I put 1 and 1 in here, I would get 1/4, and then 1 squared, and then 1, minus plug in 0, I get 0. So that's why I get 1/4 minus 0 is 1/4. Okay? So if you know this thing, then it makes stuff easier, and you can find like the work done and all that a little bit easier. Right? Because it doesn't matter how you get from beginning to end, is independent of path. All right, on this next part. So this next couple pages here is just a lot of like talking through some like definitions and so forth, and some little things here, but we get to some problems at the end. So the fundamental theorem for line integrals says, let C be a smooth curve, R of t, so some kind of vector path you're following, and from A to B. Let f be a differentiable function of 2 or 3 variables whose gradient vector del f is continuous. All right, so then we have the work done is, basically this is what we came to on the last page. So there's your equation for the work right there, and here's what we came to. You can just do plug the terminal point into the function minus the initial point into the function. That'll be the work. Okay? Whereas before, we had to do the dot product of my vector plugged into my function, dotted with my derivative of my vector, the force field, and then I had to do the dot product and do my integral. So I don't have to do that anymore if I know the original function. All right, so we can evaluate the line integral of a conservative vector field. Remember, conservative means that your thing that you're given is already the derivative of something that came before it that you can find, right? So the gradient vector field of the potential function, and that thing is called the potential function, the thing that came before your conservative vector field, simply by knowing the value of the function at its endpoints. So the line integral of del f is a total change in the function. All right, so let's go ahead and do one. So you are given the original function here. So we're given the original function, and I want to know, let C be any smooth curve from 0, 1 to 3, 0, and I want to know what's the work done when you're going along that curve from here to here. So because I'm given this problem, its original part, it doesn't matter. It's going to be independent of path. This thing is differentiable and continuous, so that means that I'm allowed to use all this information here. All right, so if I want to do the work, all I have to do is basically this information there. I got C del f dot dr. I can instead just do f of 3, 0 minus f of 0, 1. So the end minus the beginning. So I can plug 3, 0 into this problem here. So if I do that, I get 9 plus 3 times 0 is 0 plus 0 minus, when I plug in 0 and 1, that would be 0, 0, and 2. All right, so 9 minus 2. So the work done is 7. And so that makes things a lot easier because it doesn't matter what path you go, it's all going to be the same. So example 1 illustrated that as well for you. Independence of path for conservative vectors, vector fields. All right, so independence of path. C1 and C2 are two piecewise smooth curves with the same initial point and terminal point. So in general, the work right there is not equal, but the fundamental theorem of line integrals says that a conservative vector field, like in example 1, depends only on the initial and the terminal points. All right, so your work done is independent of path if these two equal each other. So basically, if those two equal each other, then you know that you had a conservative vector field if you had found those two things as well. So it kind of goes backwards and forwards. Okay. Okay. A closed curve has the same initial and terminal point. So when you have a closed curve, like if you come back to where you started, then what's going to happen? F of RB minus f of RA will be 0 because they'll be the same. So your work is independent of path if and only if this equals 0 for every closed path. So that's just kind of like denoting that little rule right there. All right. Excuse me. All right, almost done with all these theorems. Let's see. Suppose F is a vector field that is continuous on an open connected region D. Then your work is independent of path in D. If that's independent of path, then F is a conservative vector field on the domain. And there exists a function, a potential function, that your F was the derivative of. So your F was the derivative of some potential function right there. So this right there, that's called your potential. Right. And the type of function whose line integrals are independent of path are conservative. All right, so here we get to where we're going to use some of this a little bit later. If you have your function and notice that you have a p function here and a q function there, if it's a conservative vector field where p and q have continuous first order partial derivatives, so that means you can do the derivative and they're continuous when you do them on a domain, then this is going to be true. So the derivative of the x part, that's p, with respect to y, should equal the derivative of the y part, that's q, with respect to x. So it's kind of like crisscross, like backwards. So this right here is a test to see if a vector field is conservative. So if somebody says, hey, I'm going to give you this vector field, is it conservative? You do this, and if they're equal, then they are. So actually, why don't we just do that real quick? So let's just do that here. We'll skip ahead for a second, then we'll go back. So that's what this thing is saying too. So let's determine if this is conservative or not. So basically, I need to take this piece and do the derivative with respect to y. So that's my p. I need to do the derivative with respect to y. So the derivative of this with respect to y would be 1/2 x. And then I need to do the derivative of this piece, but with respect to x. So 2 times 1/4, and then knock the x down. And so that is also 1/2 x. These are equal to each other. So yes, it is conservative. Okay. So down here, determine if this is conservative of path or not, or conservative or not, independent of path. All right, so I do the derivative of my p part with respect to y. So that goes away. The derivative of this with respect to y is 4x. Then I do the derivative of this part, but with respect to x. The derivative with respect to x is 4y. And then that part would go away because there's no x's at all. So this is not equal. So that's a big fat no. Okay. All right. So that's all we had to say there. Let me make sure I got that. All right. So to show independence of path, we need to show that the function or the vector is conservative. And so to evaluate, we're going to need a potential function. So the next thing is how to find that potential function. But let's go back to these other two little definitions here. All right, this is not taking as long as I thought it would, so good. All right, so let's go down to these pictures here. These are just some like definitions. I mean, it's just things to know. It's not really like, I don't know, it doesn't seem that important, but it's just definitions of words. So something is called connected, like D is your domain. Your domain is connected if any 2 points of your domain can be connected by a path entirely in that domain. So look over here at this picture. This right here is R1. This like shaded part is R1. And so that is the only part. I can sit anywhere in that shaded part and I can get to another place in that shaded part. So like if I'm here and I want to get over there, I can get there by staying in the shaded part. Well, this is really hard to see here, but this is also a shaded part. Like that's also shaded right here. And this is R2. So R2 is like this domain area here. So this domain here is 2 different sections. And so like think of like a lake, like 2 little lakes or whatever. This is one big lake. So 2 little lakes. Can you get to this from any point in here to any point in there by staying in the water? No, you'd have to go on the land. So these 2 are not connected. So it's just kind of obvious. All right, so next definition, a curve is called simple if it does not intersect itself, except possibly at its endpoints. So simple is when you don't cross over yourself. So this one's simple, but it's not closed because it didn't connect back to itself. All right, this one's not simple. It crosses itself in a couple places, but it is closed because it finished where it ended. And so this is kind of like 2 definitions, simple and closed. And then this one right here is both. It's closed and simple. Not only is it start where it ends where it starts, it's not crossing over itself. Okay, so those are those words. So let's just go down here for a second. So your domain is simply connected, means that every simple closed curve in your domain, enclosed only point of D. I don't know what I was saying there. Just forget that sentence there. Okay. All right. So let's say true or false right here. So C. Domain C over here. Is it simple? Think to yourself. No, it is not. Right? Because it crossed over itself. So that one is false. All right. Is C closed? This area here, is it closed? Yes, it is. Or no, it's not, sorry. Because it didn't start and end in the same place. So that is false as well. So this thing is not simple and not closed. All right, letter C. D is simply connected. True or false? All right, true. It is connected because any place in this shaded little barbell, I can go from here. If I pick a point here, I can go to any place else in the barbell, and I do not have to leave the barbell. All right, I can go from here to here, like whatever. I can do anything in there. Nothing's stopping me or cut off. So that means it's connected. Is it simple? Yes, because the outer bounds don't overlap and don't like cut across itself. Okay. And it's closed actually as well. All right, so let's go back over to where we were here. All right, so probably, I'd say about 5 more minutes if you can take it. Okay. Otherwise, like I said in class, you can stop, come back later. All right, so we are going to figure out how to find their original function, or an original function. So you know that your del f, if you have the derivative, then the original is called your potential function, all right? So I want to find an original function whose gradient is this. So this is my gradient vector. This is, y squared plus 1 and 2xy plus 3y squared. So I want to find, this is my del f. I want to find what the original problem was whose derivative was this. So remember, this part was the derivative with respect to x, and this part was the derivative with respect to y. So what do I have to do? I have to integrate those things to go backwards. All right. So if this part was the derivative with respect to x, I should do the integral with respect to x of that first part. Okay, and I don't have any bounds, so I'm going to have plus a constant over here. So the integral with respect to x, so that means that these are both going to get x's. So xy squared plus x plus, now I have a constant, all right, but I also have any function of y. Like if I just had here a function of y, so I could have, so remember, if I do the derivative of this with respect to x, if I find the derivative with respect to x right here, if there happened to be something a y, like a y squared, I would never have known it over here because it would have just gone out to 0, kind of like my constant does the same thing. So remember, I have other things to worry about because we're doing like partial derivatives and stuff. So there could have been a function of y sitting over here, because these have x's. This could have been a function of y that had all y's in it, and I did the derivative with respect to x, and it just wiped itself out. It got 0, and I would never have known it was there. So I have to say that. All right, so now I do the integral for the next one, but I do it with respect to y. So 2xy plus 3y squared. So the integral here would be 2y squared over 2. So 2xy squared over 2, so xy squared. Notice the matching. Plus here gets me 3y to the third over 3, so just y to the third. Plus any constant, plus any function of x. Remember, if I was going to do the derivative of this with respect to y, then I would get this, and I get that. There could have been some function of x, and I was doing the derivative with respect to y. It could have had all x's, and it just canceled out to 0. All right, so it could have been there. Okay, so here we go. This right here, match. So great. I am going to include that in my original problem. So my function of xy, xy, is going to include xy squared. I need it. Plus, this one says I need x. Well, look at that. That can be this. And this one says I need y to the third. Well, that can count for that. So plus x plus y to the third. And then plus any constant, any like random number that could have been on there. Okay? C, or you can put the letter K, I think the book does. All right, so you can test it. Let's do the derivative in our head with respect to x. So that would be y squared plus 1. Look at that. And what's the derivative with respect to y? Well, it would be 2xy plus y to the third, or 3y squared, right there. All right, so there it is. So that's your test. And the derivative with respect to x, this part would not be there. The derivative with respect to y, this wouldn't be included. Okay, so that's your answer to this question. That was the potential function for this gradient vector. All right, so we're just going to do it one more time, I think, right here. And that's it. So I guess I was a little bit undercutting my time here. All right, so here is my vector field problem here, and so I'm going to go back and find what f was. All right, so find a function f that could have come before this function. So who is this the derivative of? Okay, so we have to do the integral. Remember, this is the derivative with respect to x, and this is the derivative with respect to y already. Okay, so this big F is representing del f. I need to know what was the equation before it. So I need the integral of 3 plus 2xy with respect to x, and I need the integral of x squared minus 3y squared with respect to y. So stop the video and do that real quick. All right, so my integral here is 3x plus x squared y plus a function of y possibly plus a constant. And down here I would have gotten x squared y minus y to the third This is super similar to the last one, isn't it? Minus y to the third plus a function of x possibly plus a constant. Okay, so my decision is that my function f of xy was this part and these two pieces plus some kind of constant. All right, letter B, so I'm going to need to go down here. Evaluate the line integral. So this was a conservative situation, and so I am independent of path. And so basically I can use my earlier discovery, I guess, that f of RB minus f of RA. So I can just do the terminal minus the initial. But it's going to be a little bit of work, like getting there. Okay. So let's see. So f of R, I am ending at pi. So R pi minus f of R 0. Okay. So let's go over here and let's figure out those things. Like, what the heck is this? So my function is right there. So R of pi would be e to the pi, and then sine of pi, and I'm just going to put comma and make it a vector, e to the pi, and cosine of pi. All right, so e to the pi, whatever that is, sine of pi is 0, so that's going to be a 0 there. E to the pi is whatever, cosine of pi is -1, so negative e to the pi. Okay. Let's find R of 0. So if I plug 0 in here, e to the 0 is 1, sine of 0 is 0, so I get a 1. E to the 0 is 1, cosine of 0 is 1, so I get a 1. This is 0, sorry. Okay, so all I have to do is I have to plug R pi, I have to plug this guy into my function, and then minus plug this guy into my function. Okay. So I have to do f of 0, 0 and negative e to the pi minus f of 0 and 1, right? Which still is a little bit of work, but it's easier than doing what we were doing before with the whole dot product and all that kind of stuff for the work. This would have been kind of gross, all these derivatives of these things and all that. All right, so I got to plug 0 and e to the pi in here. So 0 for x, that goes away, that goes away. I'm going to have to cube this part. So I have negative e to the pi cubed. Okay. All right. Let's see, minus, now let's plug in 0 and 1 everywhere. So that goes to 0, that goes to 0, and plug in a 1, so minus 1. All right, so hang on a second. I feel like I have this backwards a little bit. Just give me a second here. F of R pi minus f of R 0. I'm just checking my stuff here because on my paper I have it backwards, but I must have just done it backwards by accident. All right, maybe I'm messing up right now, but I think I just did it wrong earlier. So a negative cubed would be a negative e to the pi. 3 pi that would be, because multiply my exponents, and then minus 1. Alright, let me just make sure there's no reason why it's backwards here. Why did I put those negatives? I don't know. All right, well, maybe I'll just look at it, and if I figure it out, I'll tell you in class. All right, so there we go, and I'll see you next time. Bye-bye.